Space is vast, it's full of mysteries. One of the most fascinating is gravitational lensing. Imagine a cosmic kaleidoscope, warping and magnifying light from distant corners of the universe. That's gravitational lensing in a nutshell. This mind-bending phenomenon, predicted by Einstein's theory of general relativity, allows us to observe objects that would otherwise remain hidden from our view. Gravitational lensing occurs when massive objects like galaxies or black holes distort the fabric of space-time. This distortion bends the path of light traveling near them. Think of a bowling ball placed on a trampoline. The ball creates a dip in the fabric, causing anything rolling nearby to curve inward. Gravitational lensing is a powerful tool for astronomers. It acts like a giant magnifying glass, amplifying the light from distant galaxies. This allows us to study objects too faint or distant to be seen otherwise. By studying these lensed objects, we can learn about the distribution of matter in the universe, the nature of dark matter, and even the properties of the first stars and galaxies that formed after the Big Bang. Einstein's general relativity tells us that gravity is not a force but a curvature of spacetime. Imagine spacetime as a giant rubber sheet. Massive objects create dents in this sheet, much like the bowling ball on the trampoline. Light, traveling through spacetime, follows these curves. When light passes by a massive object, its path bends. This bending of light is what we perceive as gravity. The more massive the object, the more it warps spacetime. The more spacetime is warped, the more light bends. This bending of light can create some fascinating visual effects. We can see multiple images of the same object, distorted arcs, or even complete rings of light known as Einstein Rings. Gravitational lensing comes in different flavors. We categorize them by their strength and the scale of their effects. The three main types are strong lensing, weak lensing, and microlensing. Strong lensing, as the name suggests, produces the most dramatic effects. It occurs when a massive object like a galaxy cluster is perfectly aligned with a distant background object. This alignment can create multiple images of the background object arcs or even those stunning Einstein rings. Weak lensing is more subtle. It occurs when the alignment between the lensing mass and the background object is not perfect. This results in subtle distortions of the background object's shape. These distortions, though small, can be measured and used to map the distribution of dark matter. Microlensing is the smallest scale of gravitational lensing. It happens when a relatively small object, like a star or a planet, passes in front of a more distant star. The lensing object acts like a magnifying glass, briefly amplifying the light from the background star. Among the most striking examples of strong gravitational lensing are Einstein rings. These perfect rings of light occur when the alignment between the lensing object and the background object is nearly perfect. Imagine a distant galaxy, shining brightly in the vastness of space. Now, picture a massive galaxy cluster sitting directly between us and that distant galaxy. The gravity of the galaxy cluster bends the light from the distant galaxy, acting like a giant lens. Because the alignment is near perfect, the light is distorted into a ring shape, forming what we call an Einstein ring. These rings are not just beautiful, they are powerful tools for studying the universe. Section 5. Cosmic Magnifying Glass, Unveiling the Universe's Hidden Treasures. Gravitational lensing is a crucial tool for modern astronomy, acting like a giant magnifying glass that allows us to see deeper into the universe than ever before. By studying the distorted light from distant objects, we gain insights into the universe's most elusive secrets. One key area is the study of dark matter. Dark matter doesn't emit, reflect, or absorb light, making it invisible to telescopes. However, it interacts gravitationally. By observing how light bends around galaxies and clusters, astronomers can map the distribution of dark matter. Lensing also helps us discover exoplanets. Microlensing events, caused by stars or planets passing in front of distant stars, create a telltale brightening effect. By analyzing these events, astronomers can detect planets orbiting other stars, even those much smaller than our own. Furthermore, lensing allows us to peer back in time, observing the most distant galaxies in the universe. The light from these galaxies, emitted billions of years ago, is stretched and amplified by the gravity of intervening galaxy clusters. This allows us to study the universe's early history, witnessing the formation of the first stars and galaxies. Section 6. Cosmic Icons, the Einstein Cross, and the Bullet Cluster. There are many stunning examples of gravitational lensing in the universe, but two stand out as particularly iconic: the Einstein cross and the bullet cluster. The Einstein cross, a quasar lensed by a foreground galaxy, is a visual masterpiece. Instead of one image of the quasar, we see four, arranged in a cross-like pattern around the central galaxy. The bullet cluster, on the other hand, provides compelling evidence for dark matter. This cluster, formed by the collision of two galaxy clusters, shows a clear separation between the visible matter and the distribution of gravity. This separation is best explained by the presence of unseen dark matter, which interacts gravitationally but not with light. Section 7. Peering through the cosmic curtain, revealing the unseen. The universe is full of hidden treasures, objects and phenomena that are too faint, too distant, or simply too obscure to be observed directly. Gravitational lensing, however, provides a way to pierce this cosmic curtain, revealing the unseen. Imagine a distant galaxy, shrouded in dust and gas, its light struggling to reach us. By chance alignment, a massive galaxy cluster sits between us and this hidden galaxy. The cluster's gravity acts like a lens, bending and magnifying the faint light from the hidden galaxy. This lensing effect allows us to see the hidden galaxy in greater detail than would ever be possible otherwise. We can study its structure, its composition, and even its history, all thanks to the cosmic magnifying glass of gravitational lensing. Section 8. Microlensing, detecting hidden worlds through tiny twinkles. Microlensing, the smallest scale of gravitational lensing, is like a cosmic game of hide-and-seek, where planets around other stars reveal themselves through subtle twinkles of light. Imagine a star far away in the Milky Way galaxy, its light traveling for hundreds or even thousands of years to reach us. As we observe this star, something remarkable happens. A rogue planet, perhaps orbiting another star, passes directly in front of it. This planetary passage, though brief, acts like a tiny lens, focusing and amplifying the light from the background star. We observe this as a sudden temporary brightening of the star, a telltale sign of microlensing. By analyzing the duration and shape of these brightening events, astronomers can infer the presence of the lensing planet, even though we cannot see it directly. Section 9. Mapping the invisible weak lensing and the hunt for dark matter. Dark matter, the elusive substance that makes up the majority of the universe's mass, remains one of the biggest mysteries in modern astrophysics. While we cannot see dark matter directly, its gravitational influence on visible matter provides clues to its distribution. This is where weak gravitational lensing comes into play. Imagine a distant galaxy, its light traveling for billions of years to reach us. As this light passes through the vast cosmic web of dark matter, it encounters countless subtle gravitational tugs. These tugs, though individually small, collectively distort the galaxy's image, stretching and shearing its shape ever so slightly. By analyzing the statistical distortions in the shapes of numerous background galaxies, astronomers can create maps of the dark matter distribution. These maps reveal the cosmic web in stunning detail, showing how dark matter clusters and filaments connect galaxies across the universe. Section 10. A bright future. Gravitational lensing in the 22nd century. As we venture further into the 22nd century, gravitational lensing promises to play an even greater role in our quest to comprehend the cosmos. New telescopes and advanced technologies will allow us to study this phenomenon with unprecedented precision, unlocking new secrets of the universe. Imagine space-based telescopes far beyond the blurring effects of Earth's atmosphere, capable of detecting the faintest distortions caused by weak lensing. These telescopes could map the distribution of dark matter with exquisite detail, revealing its clumpiness and how it affects the formation of galaxies. Furthermore, advancements in artificial intelligence and machine learning will be crucial in analyzing the vast amounts of data from these future surveys. These technologies will help astronomers identify even the most subtle lensing events, leading to the discovery of new exoplanets, including those potentially habitable. Section 11. Gravitational lensing, a cosmic legacy. Gravitational lensing, once a prediction of Einstein's genius, has revolutionized our understanding of the universe. It has transformed from a curious effect to an indispensable tool, allowing us to probe the cosmos with unprecedented depth and clarity. From revealing the distribution of dark matter to uncovering hidden exoplanets, gravitational lensing continues to illuminate the universe's most closely guarded secrets. As we develop even more sophisticated telescopes and analytical techniques, the future of gravitational lensing research is bright, promising a deeper understanding of our universe and our place within it. The cosmos, with its elegant laws of physics, has provided us with a magnificent tool to explore its vast expanse. Gravitational lensing stands as a testament to human ingenuity, showcasing our ability to unravel the universe's mysteries and peer into the depths of space and time.